In recent years, holographic displays have emerged as a promising platform for next-generation near-eye displays. They offer unique advantages, including a thin form factor and vision correction, while also making significant advancements in addressing its long-standing challenges such as high image quality and computational speed. At the core of holographic display is the computer-generated holography, or SIGGRAPH. The fundamental principle of SIGGRAPH is to modulate the phase and/or amplitude of a coherent light source, such that diffraction and interference create the illusion of a 3D scene for a viewer. The SIGGRAPH is versatile enough to adopt different target distributions. Among them, layer-based targets have gained immense popularity, due to their ability to leverage the FFT-based wave propagation models, resulting in remarkable speed. Alternatively, the SIGGRAPH is capable of generating the desired intensity throughout the entire 3D volume, by constraining the intensity of all voxels. Lately, these holograms have been successfully demonstrated in experimental setup, with impressive image quality. However, most evaluations of these holographic displays have been conducted using camera-based experiments, which only consider specific viewing conditions. Unlike stationary cameras, the human eye is constantly in motion, involuntarily experiencing pupil contractions and relaxation. So it is not trivial that an approximated holographic 3D scene, optimized for a camera or an ideal viewpoint, truly provides a satisfying 3D experience for users. On the other hand, the true potential of holographic display lies in its ability to effectively provide the spatial angular information of light. The hologram can be optimized to generate desired light fields, as recently demonstrated by Choi et al. In this work, we investigate the perceptual realism of 3D scenes presented through holographic near-eye displays, while considering natural viewing conditions. We begin by testing various 3D SIGGRAPH algorithms taking into account various pupil sizes and positions. In ideal viewpoints, all algorithms provide excellent image quality for all focal states, as expected. However, when the pupil deviates from the center, the image quality degrades as it only samples a portion of the light. It is worth noting that light field holograms exhibit the highest robustness in such scenarios. They effectively preserve correct parallax effects throughout the entire eye box, as they contain accurate spatial angular information. To evaluate the effectiveness of algorithms in achieving perceptual realism, we assess them using perceptual metrics, such as FOV video VDP, across different pupil sizes and positions. This metric is scaled into just objectionable difference, as plotted on the left. Our simulations conclusively demonstrate that light field holograms outperform other techniques significantly in terms of perceptual realism. To verify this, we created a perceptual holographic testbed, which is shown on the left. On the right, we present one of the experimental results captured from this setup, utilizing a moving camera at non-ideal viewing points. Note that a light field hologram exhibits greater robustness to diverse viewpoints and accurately demonstrates parallax effects. We conduct a user study on our perceptual testbed, where subjects are presented with a sequence of stimulus pairs and asked to select the more realistic 3D option. The study is performed under various viewing conditions, including different pupil positions. Additionally, we test the viewing condition with head movement, allowing subjects to freely move their heads within an observable range of the scenes. Our study reveals that full parallax must be taken into account for holographic rendering, in order to provide perceptual realism across all viewing conditions. What's even more interesting is that this trend persists even at the center of the eye box, where the distinction becomes nearly imperceptible in captured images as well as simulations. The prevalent SIGGRAPH pipeline, reliant on naive low-pass filtering, overlooks the complex human visual system, leading to no variance in the retinal image despite eye movements when eye box support is minimal. Our research motivates a compelling case for incorporating the human vision, such as the directional sensitivity of the retina, into the rendering process to enhance the perceptual realism of holographic displays. Our work provides crucial insights on the effectiveness and realism of SIGGRAPH algorithms that will help guide the community toward passing the visual Turing test of displays, using future holographic light field near-eye displays.